some logistics before we start with the presentations. This is Paige Johnson with American Wind Wildlife Institute, and welcome to this WREN webinar. So just before we get started, I'll go through a few logistics notes. For sound, you should be able to hear us through your computer. If you're having any technical trouble with the webinar, you can email me. My email is pjohnson, that's PJOHNSON, @awwi.org. You can also send us logistics questions through the questions box in the webinar room. And if you are listening on the phone, please make sure to mute your line so we don't get any background noise. We'll be doing a Q&A session after each presentation. So if you have a question for the presenters, please enter it in the Q&A box at the bottom right-hand corner of your webinar screen. You can type your question into the dialog box at the bottom and click the button at the right or hit enter to send it. You can enter your questions at any time during the presentations, and at the end of the presentation, we will read the questions out loud for the presenters to respond to. And you will only be able to see questions that you submitted in the box, not those submitted by others. And finally, just a reminder that we will be recording this webinar, and it will be available on the WREN website shortly after the webinar takes place. So with that said, I will turn it over to Elise to introduce the speakers.
Okay, thank you, Paige. This is Elise DeGeorge with the National Renewable Energy Laboratory. Welcome to our WREN webinar number 12. WREN is the name for International Energy Agency Wind Task 34, which consists of 11 member nations. WREN stands for Working Together to Resolve the Environmental Effects of Wind Energy. We launched this webinar series in 2004. It's comprised of quarterly webinars developed to support WREN's goals of facilitating international collaboration to advance global understanding of the environmental effects of wind energy development. All of our webinars we've held to date, and all the ones that we're holding in the future, will be housed here at our WREN hub, and the URL is located here, tethys.pnnl.gov. So that includes all transcripts, slides, and audio of each of the webinars held to date. Today's webinar is on upscaling wind and wildlife individual interactions to population level impacts. And we're lucky to have three great speakers. We have Kimberly Bay and Shay Howlin with West, and Finlay Bennett with Marine Scotland Science. Kim and Shay will talk about West's development of a quantitative assessment of the direct effects of wind energy on small passerines and diurnal raptors in North America. And Finlay will present a summary of a manuscript produced by the WREN Collaborative on individual to population impacts. A little bit about our speakers. Kim Bay has worked with West since 2001. She has a BS in mathematics and statistics and an MS in statistics. She developed and managed several large cumulative databases, which enables West to utilize data regarding wind-wildlife interactions from over 20 years of research across the U.S. to assess potential risk or impact to wildlife from wind energy development. Shay Howlin has been with West since 1999 as a consulting biometrician. She has a BS in wildlife and fishery science and an MS in statistics. She's been involved primarily in ecological monitoring studies and analyses, designing and estimating resource selection functions, conducting data analyses for wildlife research, and analyses associated with natural resource damage assessment cases. Finally, Finlay Bennett is team leader of the Renewable Energy and Environmental Assessment Program of Marine Scotland Science, which is part of the Scottish Government. He's also a member of the WREN Group and chairs the ICES Working Group on assessing the effects of marine renewable energy. He has been working on assessing the effects of wind energy development for over 15 years, previously working for the Joint Nature Conservation Committee and Scottish Natural Heritage, both statutory advisors to government on nature conservation issues. So that's a little bit about our speakers today, and without further ado, I'll turn this over to Kim and Shay. Thank you.
Good morning, everyone. This is Kim. Thanks, Elise. Thanks, everyone, for taking the time to join the webinar today. Shay and I are going to go discuss the methods and results of two manuscripts. One manuscript is published in PLOS ONE, discussing the impacts of small birds or passerine population impacts from interaction with wind farms. In addition, we have a manuscript in prep with a similar topic related to diurnal raptors and their population impacts from interaction with winds. As Elise mentioned, WES has developed and populated a large cumulative fatality database that houses data from over 300 post-construction monitoring or PCM studies. So the database houses information from all studies that we have public access to. Not all of those studies are appropriate to be used in meta-analyses. Some of the standard things that we look for is that the study design has a representative sample of turbines at the wind facility, including bias trials of known biases associated with these searches, including searcher efficiency bias related to the number of carcasses that a searcher finds that are available to be found. The availability of these carcasses is determined based off carcass removal trials or scavenging trials, where placed carcasses are monitored to determine the length of time that they last in the field. And then how these biases interact with the study design, in particular the plot size and the search interval length. As I mentioned, we've done this analysis for small birds and passerines and diurnal raptors, but the cumulative fatality database could be used to do similar analysis for other major bird types or sensitive species in the future if there was a need or a desire to do so. I'm going to pass it over to Shay now to discuss the specific analytical methods used in the manuscripts, and then I'll come back later and discuss the results.
Okay, good morning. This is Shay Hallen, and I was the analyst for the Raptor Analysis, which was based on the Passerine Analysis, so I'm familiar with the methods, and I will describe those in more detail to you. Our overall goal of this research was to estimate the annual number of passerines and raptor fatalities due to wind using data from post-construction monitoring studies. So how did we select the studies? As Kim said, there are over 300 studies in our database, and not all of the studies were public studies. So first of all, we limited our research to studies that were either in the public domain or we were given permission for to use. So we reviewed these studies for the study length, the methods, and the fatality estimator formulation. And when we get all our studies together, we went through a process that I'll describe here of standardizing the fatality rates from each study so that we could summarize them in an average context and then compare to the population sizes for the small birds and the raptor species. Trying to change the slide. We got it. So more specifically, we included studies with fatality estimators formulations that had been involved in our previous research on the relative biases of these estimators. So there are a handful of estimators from common estimators to quite obscure estimators, and we limited to those that were more common. We know under certain field conditions, estimators tend to have directional biases and give us predictions that are either high or low. So the other features of these studies were, as Kim described, we limited to studies
that had the biased trial data, so the searcher efficiency biases and the carcass removal bias. As Kim mentioned, we conduct bias trials to correct the observed number of carcasses that we find in the field. So in case you're not familiar with it, the searcher efficiency trials, we put birds out and see if the searchers find them, and it's intended to estimate the probability of detection. And the carcass removal trials, we put birds out and see how fast scavengers remove them, and it's intended to estimate the probability that they are available to be found. And so we combine those two correction factors to something we call pi hat, which is the probability it's available to be detected and it's detected. We use that pi hat in a Horvitz-Thompson-like adjustment to increase the estimate, and it increases the observed number we found, and we end up with a adjusted number of fatalities per turbine. Older studies without trial data adjustments were excluded from our research. And seasonality, we required the bird studies to cover at least 3 seasons, spring, summer, and fall. Studies that were not included are those that we couldn't standardize, older methods, search intervals that were extremely large, or studies conducted at the older generation facilities that aren't being built anymore and weren't really a part of what we wanted to make inferences to. So since the idea behind the Menace analysis was to standardize these estimates so that we could then combine them into an average fatality estimate for the entire area. For passerines, we did this by regions in North America, and I'll show you that map in a minute. For raptors, we did this, we split the United States into the eastern and the western parts of the country. So we standardized for plot search areas. We know this is important to account for because estimates depend on how large an area is being searched, which is related to the turbine size. So using the Holomere ballistics model, we standardized all the estimates to the same size plots. And then we standardized the survey length, assuming that observed fatality estimates during the seasons that were searched were equivalent to the seasons that weren't searched, and we got annual estimates for every study. And then moving on to the adjustments, so for some studies, just for the passerine research, for some studies we had to infer a passerine estimate from the all-bird estimate that was presented in the report. We do this using the percentage of observed carcasses in the actual observational data, and we adjust for the probability of detection for the different sized carcasses. For the raptors, we had to calculate expected number of raptors for several studies that had no raptors. So raptor fatalities are akin to rare events, and so we have a lot of what we consider false zeros in the database. So we imputed the probability of observing a raptor given the probability that it was available and detected, and we calculated the expected number of raptors for several studies. Lastly, we have alluded to the corrections we made for estimator bias. So we studied the biases of 5 or 6 of the commonly used estimators and the study of characteristics associated with the bias. So we know when we have slow carcass removal and frequent search intervals, we get a different bias than when we have fast carcass removal and infrequent search intervals. So we undid these biases by applying a correction factor to each study based on their search interval, carcass removal, and thief. And since we know these biases, the biases associated with these estimators are not without variance, we incorporated a range of the bias adjustment in the form of a low and a high adjustment. And so the end result was each study gave us an estimated number of fatalities per year for each species and per megawatt. So we averaged these estimates across first across multi-year studies at a facility and then across facilities. And so, for example, the small birds, we had approximately 7 leaf facilities that we were averaging these estimates over. And then we take the average per megawatt and we attribute that, or we scale it to the installed capacity in the United States and Canada to get population impacts. So here's the reference for the Passerine work. There were 116 studies, so we had multiple years of studies at wind farms. And so you can see the spatial extent of the studies here in the figure on the right, and the black numbers represent the number of studies in each of the avifaunal biomes in North America. We had very little data in the Southwest, so we actually lumped that in with California. And then for the Raptor analysis, we looked at the raptors in it with a just for the United States, and we broke this into a eastern and a western context. So the yellow dots represent the eastern, and the purple dots represent the west. And so we had 146 studies. This was a more recent publication. There's more studies, and it constituted 85 wind energy facilities in the United States. So again, we compare these estimates we get for, it was North America for the passerines, and just U.S. for the raptors, but we compare these estimates to the population of birds in North America that has been estimated by the Partners in Flight database. So I'll hand this back to Kim for a description of the impacts we found in this study.
Thanks, Shay. The following table gives you an idea of why we started with passerines and diurnal raptors. The majority of carcasses found at wind facilities are passerines, which is not surprising given they're also the most abundant in the population. Passerines represent approximately 60% of the total carcasses, followed by diurnal raptors at 8%. And if you add in owls and vultures, you get approximately 11%. As I mentioned previously, this is an analysis that we could complete on other bird types or species of concern if there was a need or desire. As Shay mentioned, when we did the analysis for this Passerine manuscript, the 70-plus facilities represented 15% of the third quarter 2016 operating capacity in U.S. and Canada based on the WIA and CanWIA websites. After completing the standardization that Shay spoke of, we found that on average, passerine rates range from 2.1 to 3.4 passerines per megawatt per year. This was the average across the biomes. To extrapolate the total impact for the U.S. and Canada, the biome-specific fatality rate was extrapolated to the number of megawatts within that biome, and then that information was summarized across the biomes to come up with the U.S. and Canada total of 186 to 319,000 small passerine fatalities per year across U.S. and Canada. Again, this is representing the megawatts through the third quarter of 2016. Along with being able to look at total passerine impact across the U.S., we were also able to look at calculate species-specific fatality estimates and compare that to the Partners in Flight population information. What we found in our study is that all of the passerine species showed less than 0.1% impact on the annual population. The three highest species were tree swallow, black-throated blue warbler, and horned lark, but like I mentioned, all of those had a low population impact ranging from 0.05 to 0.06% of the population is in fact impacted annually by wind interaction. So in general, wind interaction for passerines tends to have a low population impact. The following graph represents the eastern biome and the estimates that came from those facilities for a particular year. The graph gives you an idea of the variability in the estimates in general, but it also gives you an idea of the biases that we adjusted for. The top of the blue bar is the most conservative estimate after our bias corrections, and the top of the green bar is the less conservative estimate, again, based off the biases. Moving on to diurnal raptors. When I speak about diurnal raptors, I'm not including owls and vultures. Given that this manuscript is in prep and includes a larger data set of over 80 studies, it represents a slightly larger percentage of the capacity megawatt through the third quarter of 2016, up to 16%. Again, after standardizing, as Shay discussed previously, we found that the fatality rates across the U.S. ranged from 0.1 to 0.2 diurnal raptors per megawatt per year. This, again, was arrived at by averaging the east and west estimates. And again, extrapolating to the number of megawatts across the U.S. resulted in a total of 8,300 to 17,600 raptors per year in the U.S. Using the same assumed fatality rate results in approximately 1,200 to 2,500 raptors per year in Canada as well. Again, this represents the megawatts operating in third quarter of 2016. Similar to the passerines, this graph gives you an idea of the variability in raptor estimates across the U.S. Again, the top of the blue bar is the most conservative estimate based off the bias adjustments, and the top of the green bar is the least conservative. Again, just want to stress that these are not confidence intervals, but rather just bias adjustments and a range of possible fatality estimates. Similar for passerines, we were able to determine species-specific estimates and compare that to population information from partners in flight. Again, all of the raptor species had less than 1% of their population impacted annually. Peregrine falcons and American kestrels were the two species with the highest population impact, ranging from 0.42 to 0.55% of the population impacted annually from wind. In order to summarize what we would expect the total number of birds impacted by wind interaction, we used a similar idea, making some general assumptions, trying to be conservative in nature. We assumed that the fatality rate of non-passerines and non-raptors ranged from 1.1 to 1.8 megawatts per year. Again, extrapolating to the megawatts through third quarter of 2016 resulted in a total of 96 to 156,000 other species per year. And adding up the passerine, raptors, and other species results in the total annual impact of all birds ranging from 292,000 to 495,000. Again, these are making some general assumption for the other bird species. Again, these are also impacts from the wind interaction. I'm going to pass it back to Shay to discuss other possible interactions, mortality interactions, and to finish up the presentation.
Okay, so in this slide we compare our wind energy fatality estimate to other sources of bird mortality. Concerns with songbird population threats and mortality come from many sources. Habitat loss and climate change are usually identified as top threats, but sources of direct mortality, such as those listed here, collisions with man-made structures, buildings, windows, fences, transmission lines, communication towers, turbines, vehicles, etc., they place additional pressures on songbird populations. Recent estimates suggest mortality from cats is one of the highest sources of direct mortality. Other anthropogenic sources of mortality, such as oil spills and pesticides, have a significant effect, as do some of the non-anthropogenic sources, natural disasters, predators, disease. So you can see here that the wind energy estimate, although it's probably one of the most precise in this list, it's also one of the lowest in this list. And we'll note also that most of the fatalities in this list are violations of the federal MBTA law. So our conclusions, so the wind energy industry has very precise estimates of mortality compared to other direct mortality sources. We did find variation among the regions, and we also found that when you compare these estimates to the population sizes, the impact is quite small, but there are also questions of cumulative impacts of all sources, which we're not able to address here. And just a quick acknowledgement of to the wind energy companies, and also American Wind Wildlife Institute, AWWI, provided funding for this, both studies that were presented here today. So Elise will lead us through questions if we have any.
Thank you, Kim and Shay. I don't see any questions at this time. Oh, got one coming. What is the source of the data for the other sources of mortality to birds?
We provide those references in both manuscripts. There are various sources for the different mortality. I could add that to the presentation that's posted.
Great, thank you. Another question. Raptors such as peregrines are long-lived. What is likely to be the population consequences of this mortality that is likely to be additive to other causes of mortality?
As we acknowledged, we are aware that there are other sources. We really just looked at the impact from wind. I do think it is a worthy topic to look at what the cumulative impact is, but that was not the intention of this particular analysis.
Okay, great, thank you. Another question. On your human sources of bird mortality slide, are those for the U.S. or are they global estimates?
Most of them are U.S. There are a couple that include a Canadian, but most of it is related to U.S. only.
Okay, thank you. Another question. Is there any information available on birds' abilities to fly out of the search area before mortality occurs?
That is a good question. I would say that that is not well known across species. I think that there's some assumptions for some of the larger raptors that they may, when they're paying attention, may avoid. But again, not necessarily covered in this study and something others are looking into.
Well, great. Those are all the questions I have right now. People can continue to put questions in and we'll address them after Finlay's presentation. Oh, two more. Here's two more. You showed that some facilities have much higher fatalities than others. Do you know why that is?
We do see that the variability not only within the biomes but across the biomes. I think there's lots of possible reasons why. Sighting could be one, but we have not necessarily studied what the factors are that causes the higher fatality rates.
Okay. Another question, was there any information on the differences in life stage, for example, adult or juvenile, for mortality estimates?
No, the data that we have, though we try to collect as much information as possible, identifying adult versus juvenile, obviously for passerines, it's not something we took into account.
Okay, and this next one is a comment. The human sources of bird mortality are not comparable. For example, the number of cats is much higher compared to megawatt and turbines, and usually a cat doesn't kill golden eagles. Do you want to respond to the comment?
Yeah, that sources mostly pertains to passerines. Some of the other sources that we put in there, including power lines. Power lines are more, raptors are more susceptible to power lines than, say, passerines. I would also say that the estimates for wind are have been studied and standardized, where a lot of these other sources is more of a desktop review with maybe not with less standardized methods. So I think that though these estimates, the comparability may be questioned, there's still ability to say that wind is much less impactful than some of these other sources.
Okay, great. Thank you. Those are all the questions we have right now. We'll now turn it over to Finlay Bennett.
Okay, hello everyone. Hopefully the presentation is just loading up. Here it is. So that was a really interesting presentation there, and it shows what can be done when you have a long-term data set that's used standardized approaches and gives you the opportunity to do a meta-analysis and come to some of the results that have just been presented there. So in my presentation, I'm not going to do that. I'm going to take a step back and look at, review a number of issues associated with assessing the impacts of wind farms on wildlife populations that are likely to be of relevance essentially to policymakers as they want to move towards upscaling wind and wildlife interactions to population level impacts. So firstly, to begin with, it's important that I acknowledge the work of some of my co-authors on whose behalf I'm giving this presentation. So thank you to Romay, Liz Masden, and Muriel Perron. We're all based at institutions in Western Europe, and perhaps that will bias some of this presentation. I'll leave it for you to judge. But anyway, we've been working under the umbrella of WREN to produce this manuscript. And I gave this presentation recently at the conference on wind and wildlife in Portugal. So if you were there, I'm sorry, but this is a bit of a rerun of that. But the manuscript submitted to the journal Renewables and Sustainable Energy Reviews, but it's not yet accepted. It's currently under review. But The starting point for producing it was a need identified through WREN to review how population level assessments are undertaken, some of the challenges associated with assessing impact, and indeed with verifying the magnitude of impacts that are assessed to be occurring, and what policymakers can do to make improvements on some of these issues. So this is what I'll cover, the main issues identified by the writing team. Firstly, I'll set out why we consider it is important to upscale assessment of effects from individual animals to population levels. I'll then consider some of the theoretical foundations associated with relating pressures such as collision risk to the population level, and then cover the issue of defining populations for the purposes of assessment and reviewing methods that are used for assessing the overall population level impact based on these assumed effects. And I'll then move on to consider some of the techniques that are associated with verifying whether the assessed change is actually occurring or not, and also give consideration to impact thresholds and how these can be applied for the purposes of decision making. And the presentation will finish with a summary and some consideration of future directions for policy and overall conclusions. And before I go on, I should point out that the WREN group are considering a number of other topic areas, including one on the assessment of cumulative effects. And the issue of cumulative effects is obviously very heavily intertwined with this presentation, and I refer to cumulative effects a few times, but we are here clearly considering a much wider set of issues. So, why upscale from individuals to populations? Well, the assessment of loss of individual birds, bats, marine mammals or fish has the potential to give rise to population level change. And the licensing frameworks that we use require developers to provide information to the regulator or decision maker, and these have tended, with some notable exceptions, to focus on individual wind energy developments. And these will obviously have a very restricted spatial and temporal scale of assessment, usually of the effects upon individual animals. And yet the fast rate of wind energy development presents a number of challenges to policymakers who will need to balance the costs that wind energy must inevitably have on wildlife with also some of the benefits that wind energy provides wider society. So one of the first challenges is ensuring that decision makers are well informed about the potential population level consequences through pre-construction assessments. Secondly, verifying the magnitude of impacts on wildlife that is actually occurring from operation of wind farms. And thirdly, if necessary, constructing ways of mitigating impacts. We consider that overall these issues will be more effectively addressed by upscaling to population level assessment where we can do this. So on the left of this slide, I've just listed some of the pressures that are that we associate with wind farms. I don't really want to dwell on those in any detail. I want to focus on the diagram here. Some of the theoretical response mechanisms of populations. So within metapopulations, migration of individuals from good quality source habitat in the top left of the figure to lower quality sink habitats in the bottom right can help stabilize the demographic dynamics of a population. And if wind power plants are located in good quality habitat, this may change such sources into sinks. Ecological traps may occur when animals are falsely attracted to low-quality habitats with consequences of reduced fitness, survival, or reproduction. And perhaps a wind energy relevant example would be if bats misinterpret turbines as some form of attractive habitat, whether that be trees, or even looking at some of the work by Amanda Hale to look at the hypothesis that some bats mistake the smooth surface of turbines as a surface of water. And conversely, perceptual traps may occur when high-quality habitats are avoided when perceived to be less attractive. And also from a theoretical perspective, the way in which the dynamics of a population are impacted by wind energy development will depend on the life history strategy of the species of concern, whether we're talking about relatively R-selected passerines or the more K-selected raptor species that live longer and obviously have lower productivity rates. But we should observe that our empirically based understanding of density-dependent responses to pressures is usually very limited, and so we can't always say for sure whether there will be a compensatory response to a pressure or whether it may indeed be depensatory. So we need to define what we mean by a population, and at one level that's quite a straightforward thing to do. We suggest that the definition is a group of individuals from the same species which live in the same space at the same time and reproduce. And the figure here is illustrating meta-population dynamics, and we can expect the population response to wind energy development to be influenced by the spatial and temporal scales at which we've defined the population, which makes the definition important. Delineation of the population is unlikely to represent the true biological population, but rather relate to other attributes required by the assessment. For example, the wording of legislation or societal criteria or indeed human perceptions. Looking from a conservation perspective, biogeographic or international scales over extended timeframes may well be the most appropriate. And there will also be a need to consider the conservation status of the population, including any variation in the importance of the population to regional, national, or biogeographic scales. So, a variety of modeling techniques can and are used to predict impacts, and these cover a range of complexities depending really on the data and knowledge availability. And the figure here is illustrating the growth rate of a red kite population, a diurnal raptor. On the y-axis, we see the population growth rate, and how it may be changed by different wind turbine numbers and design scenarios. So the red lines are for a spaced out configuration in the landscape, and the green lines are for aggregation of wind turbines into wind power plants, which was assessed here to have a lower impact on the growth rate. And this is an example of assessment using an individual-based simulation model. So IBMs can follow the birth, death, and movements of all individuals within the model domain in discrete time steps. And the overarching preface of these models is that the processes affect the behavior and fate of individual organisms, and from there the properties of the populations emerge. And whilst appealing, we have to observe that the data required seldom exist, and the processes are often computationally intensive. So as an alternative, matrix population models or some other form of population modeling can also take into account the life cycle of the species and can provide a flexible framework that allows for a simple or complex approach depending on the available data. So these are often used instead. But the simplest method that we see being used is to sum the number of individuals impacted and extrapolate that up to the population level using a combination of available data and expert opinion. Once we've assessed impact, we may well find that we have very limited confidence in the accuracy of our assessments. So we use post-construction monitoring to improve the knowledge base related to the assumed effects. And firstly, choosing study design that can meaningfully answer the question is a key issue. And the example illustrated here shows the results from a before-after control impact or BACI design measuring the long-term effects of an offshore wind farm on fish communities. But we should observe that for many of the questions that we will be seeking answers to, more advanced forms of spatial analysis are likely to give the best quality of information, as they will be able to describe both the underlying ecological gradients across a site and the spatially explicit change arising from the pressure, And this is important when we're dealing with very high levels of natural variation, and we want to be able to detect the effect in amongst all that variation. And the next slide identifies a second key issue associated with verifying change, which is the amount of data that we should collect. Where a population has a high conservation value, this can provide us with something of a dilemma. On the one hand, we do not want to expose the population to too much risk of change, but on the other hand, if we are to become better informed about the risks to the population arising from our activity, we need to be able to more accurately measure the changes that are occurring. So monitoring would ideally estimate the power to detect change. Looking at the bottom row of the figure illustrated here, too often wind power plant monitoring studies report no significant difference, but do not account for the likelihood of falsely identifying no change when change has occurred. If a power analysis had been undertaken and there's a low power to detect change, we would obviously have a reduced confidence in the finding of no significant effect. And it has been demonstrated in reports that underpowered studies are creating an environment where we have data-rich but information-poor or drippy monitoring, which is something that we need to move away from. And obviously the kind of meta-analysis we saw before is one technique for achieving that. So setting impact thresholds, if wind power plant impacts are assessed to be negligible, then it may not be immediately obvious why this step is required. However, as the number increases, so too will the likely impact, and at some point a management decision does need to be made about the acceptable level of impact. So the figure, I hesitate to call it a figure, perhaps a cartoon on the right, illustrates some of the theory underpinning the use of what we call utility thresholds. These will be vital rate values beyond which usually harvest-based theories tell us substantial changes in the management objectives for the population will occur. And the most commonly used fixed rate harvest strategy in our context is potential biological removal. An attractive feature being then that they seek to relate population trends to losses that in theory at least will be identified as being sustainable. But a note of caution that I made earlier about how different populations can have different density-dependent responses. Ecological thresholds are specified using a population metric as an output from a population model. For example, we saw earlier the use of the growth rate value. And these can also be used to derive thresholds, which will essentially be arbitrary, such as a percentage change. Thirdly, decision thresholds will combine various sources of information, including some of the above information, to set values that prompt specific management actions. And these should engage stakeholders to assess the trade-offs in social, economic, and environmental objectives. And we should observe that although it is possible to predict likely changes or to set thresholds based in theory, it is ultimately going to be societal acceptance that determines final threshold values, which is why the decision maker is so often a politician, a democratically elected representative. So in this slide, I want to summarize some of the issues I've covered and just identify some other issues that we'll need to consider going forward. So if you look on the left-hand side of the slide, we see the risk to populations depicted as a combination of likelihood and magnitude of assessed impact. And this sets the overall context for all the steps that follow. A key issue is the need to reconcile conservative or precautionary approaches with more risk-based approaches. And this, to some extent, requires a balancing of competing principles. The next set of boxes identifying a need to choose spatial and temporal scales, and this leads into the red box in the center of the diagram, which is identifying a need for developers' individual project assessments to be reconciled with an understanding of cumulative impacts, which will often inevitably be the focus of the regulator or decision maker's assessment. And we question the extent to which project-based thresholds can ensure population perseverance at the desired levels. We argue that taking account of the cumulative effects is of increasing importance. And then on the right-hand side of the diagram, we set out the steps associated with monitoring predicted effects and the use of impact thresholds within an adaptive management approach. And we believe that the learning by doing cycle will grow in importance as concerns about cumulative impacts increase with increased levels of development. So too will we want increased levels of understanding about how to manage potential effects. So in conclusion, we expect risk-based approaches to be increasingly informed by assessments that upscale from individual to population levels. We expect more advanced methods such as individual-based modeling to be used to predict impact as better data become available, and increased use of techniques such as gradient analysis to validate changes that are potentially occurring based on those assessments. And we see this happening within an adaptive management approach that will deliver progressive improvements in our knowledge base for decision making as the actual impacts of wind energy increase with increased development. And lastly, we note the necessary balancing of costs can only be achieved in the context of risk of change to populations being tolerated at levels that are sufficient to enable robust monitoring of the potential effects of wind energy. So societal tolerance of risk and the necessary tolerance thresholds of change to improve our knowledge base may well on occasion be a key determining factor for the resolution of wind and wildlife conflicts. So that concludes my presentation. Thank you.
Thank you, Finlay. That was a great presentation. If anyone has any questions, just type them in. I'll wait a minute. While we're waiting for people to type in their questions, Kim and Shay, there is a question here that I did miss. We moved into, I think it was being written as we moved into Finlay's presentation. So if I can, are you there, and can I ask you another question on your presentation?
Sure.
Okay, great. Studies show that bald and golden eagles are increasing in number in many locations. Is it possible to incorporate this into the meta-analysis?
Bald and golden eagles present a unique problem. When the manuscript comes out, there will notably be, it will look strange that we don't have an estimate for bald eagles. That's because there are not a lot of publicly available studies on bald eagles that have resulted in actual a found carcass. So no, we have not delved into that. And again, I'm not sure using the partners in flight information, obviously that is a little dated at this point. We could look at different references for population data for those two particular species. We can think about how to address that in the manuscript since it is still in prep. So I didn't really answer the question, but no, we have not taken that into account to date.
Okay, thank you. And there, Finlay, there's a couple questions here for you. Should this be driven top-down by regulators or pushed up by developer needs?
I think that question maybe goes back to this slide that I hope everyone can see, and the red line in the middle. There needs to be it needs to be a bit of both, in my opinion. It can't just be one or the other. I think we recognise that the regulators will have slightly different requirements from developers, so there always needs to be a kind of reconciling of those requirements. So that's hopefully answered your question. Thank you.
Thanks. And here is another one. How should precaution be considered during analysis or during interpretation of impact?
Yeah, that's a really good question as well, because in practice, at least in Western Europe, it kind of happens at both stages, and indeed during the analysis it can happen at multiple points depending on individual parameters and models, and tending towards a more precautionary estimate or conservative estimate, which then inevitably results in the criticism of assessments being overly precautionary. And that well may be the case, but it creates an inherent driver for us to apply adaptive management approaches to learn and improve as we go on. I think in the ideal world, we would have perfect data going into these models, and we wouldn't really need to have that tendency to have precaution built into the analysis. The precautionary principle could be applied by looking at the endpoint results of an assessment, and the decision maker could make their precautionary judgments based on just that one step. But the truth is we're quite far from that at the moment.
Okay, thank you. This is a question for Kim and Shay. It's a little long, so if there's any sections you need me to repeat, I'm happy to do that. The number of fatalities per species was shown as a percentage of the population. It looked like population was defined as the entire number across the U.S. How biologically relevant is this population definition? Are there not subpopulations that may experience higher levels and therefore be more vulnerable? And I'm having trouble seeing the rest of this. Hold on. Paige, can you help me out with seeing the bottom of this question?
Sure thing.
Thank you.
The last aspect of the question says, has there been any investigation at this finer level?
That is one of the reasons that we did look at the data at a biome level in terms of determining what the impact was at that level, and then summed across that. We are aware that there could be small areas of impact that would influence the population of that population more than the general. But we did not look into those fine details. But that is one of the reasons that we did everything at a biome level for the passerines. But for the raptors and how they use the land, we obviously used a larger region.
Okay, thank you. We'll wait a couple more seconds here. I don't see any other questions right now. Yeah, I think we're at the end of our questions. Paige, if you could put up that last slide. Thank you. So thank you all for joining this WREN webinar. And thank you so much to our speakers, Kim, Shay, and Finlay, for very interesting presentations. As I mentioned earlier, we will be posting the webinars on the WREN hub at tpis.pnnl.gov. And if you have any ideas for future webinars or any comments or questions, you can address them to WREN operating agent team of Karen Sinclair, Andrea Copping, or Jocelyn Brown-Saracino, and their email addresses are shown here. We hope you'll join our next webinar, which is taking place in mid-January on the topic of smart curtailment. So thank you again for joining this webinar.
All right, thank you, everybody. Bye.
Thank you.
Thank you.